Welcome everyone to our usual Wednesday seminar. And today is this time is the first seminar this term. So today we are happy to hear Yulia Ageeva, who will tell us about the new approaches to about the Callan-Symanzik renormalization approach.
Okay, thank you very much. Hello, everyone. First of all, I thank the organizers for the possibility to give this talk. I'm very glad. Thank you. And yes, today I do some, I guess, detailed review with some technical moments on so-called finite formulation of quantum field theory, or sometimes I will call it as a Callan-Symanzik approach, Callan-Symanzik method, etc. But everything will be about renormalization in quantum field theory. Okay, let me start with the main idea. And this main idea actually, what I will talk for now is some technical things, how to derive these equations, Callan-Symanzik equations, which we will use to compute green functions within finite approach to QFT. And in the last part of my talk, I also briefly talk about the motivation. Why do we need this new method? So I guess that this is the best way to understand everything from my point of view. So let me start from standard approaches to quantum field theory to renormalization within standard methods. Usually when we start to calculate loops, we usually face with divergent integrals. So let me stick to the following model, 5-4 massive theory, real scalar field. And for now, I will talk about bare Lagrangian, bare scalar field, bare mass, and bare coupling constant. The metric signature reads through all talk as follows. And just let me remind very standard things which all of you know. When we start to evaluate tree-level green function, 2-point and 4-point green function, we obtain propagator or inverse propagator. Oops. And standard vertex Feynman rule. And when we go further and consider one loop contribution to this function, we arrive to something divergent. Both this integral, this one and this one, surely, and we know that they diverge quadratically and logarithmical way. So, however, we know that both these functions relate to things that we can observe, to cross sections and etc. That's why at the end of the day, this function and everything we observe must be finite. So what happened? We arrive to something divergent, but at the end of the day, we must obtain something finite. But we know that we can regularize these infinities and renormalize our theory 5-4 in my talk, for example, and everything will be okay. We arrive to finite green function, of course. So this is the standard program regularization of infinities, and then write down counter terms to the Lagrangian and subtract the found divergences. And at one loop level, we usually arrive to the following answers for 2-point and 4-point correlation functions. So here we don't see anything divergent, and lambda 1 and m1 is something finite as well, physical or renormalized. The main point is that this is finite parameters now, and gamma 2 and gamma 4 as well finite. So everything is okay. We start from something very well known from 5-4 Lagrangian. And at the end of the day, we also can obtain finite answers. So this is the standard program. However, oops, let's think about intermediate divergences. From my point of view, they can looks not so very natural, because then people start to consider some theory. They start from actually from something finite as well, from some Lagrangian. Why it should contain something infinite? I don't know. And at the end of the day, we also compute cross sections and many other things we can observe, and they also find. So from this mapping point of view, we start from something actually finite, and we should finish to something finite. Why we should meet something divergent on our way? So from this point of view, maybe we can find some other formulation of quantum field theory where we can go through the whole way of calculation and never meet divergences. And actually, there is these formulations of quantum field theory, and one of them is Callan-Symanzik approach. And actually, this method has been invented already in past days by Callan. In his course of lectures, I can send you them if you want. And but here he designed these and derived these equations in order to prove the validity of multiplicative renormalization program. However, it turns out that these equations, together with boundary condition, together with renormalization boundary condition, one can use them to derive a green function in a fully finite way. So many next slides will be dedicated to obtain these differential system of differential equations. And next we see again on simple toy model of 5-4 model how to use them to evaluate something, to evaluate green function and never meet divergent Penman integrals. Okay, again, I write down our model. We stick to zero index through all my talk. We'll refer to bare values, okay? And the main idea of this approach is that if you take a propagator in this metric okay, write down it in any metric signature and take the derivative of with respect to bare squared mass, you find out that you obtain two propagators. And if you remember the integrals, which I write down in the very first slides, you find out that you reduce the degree of divergence acting with such an operation on whole integral or on propagator. So using only this very simple idea, acting with this differentiation, you can reduce the degree of divergence of your Feynman integrals. And you may act with this action with this operation as many times as you wish. This will be very important also in what can. Okay, so let us denote this operation, differentiation with the squared mass, as theta operation on the propagator. The definition of this theta operation is right down on the slide, and we define it with also minus imaginary unity. One can think about this action as about adding some insertion of some operator which carry zero for momentum. For example, of insertion of such an operator into any diagram we consider. For a while, let us forget about this definition and think about what is the Feynman rule for this operation. Actually, this very simple. For example, you consider the following diagram. Oops, sorry. As usual, you have propagator here and phi 4 lambda vertex. Then you add the theta operation, act with theta operation on this diagram. You can denote this action with the cross, new vertex. And it turns out, after calculations, that the Feynman rule for this action of theta operation is just split or just writing two propagators in this case and multiply your whole integral by -1. That's it. So algebraic representation of theta operation is as follows, and write down in the center of the slide. And diagram definition of this operation is also right down here and comes with the following Feynman rule. Okay, as I already briefly mentioned, is that actually this integral for two-point correlation function diverges quadratically. It means that if we take only one cross here, we never obtain something finite. We obtain logarithmically divergent something. So it means that in this case, we need to act with two crosses, act with theta operation twice. After that, we obtain, in this case, finite something. It means that sometimes in some theories, and even in the simplest case, in the case of phi 4 theory, we need to define something like this. So we define the action of two theta operation on our green function. Okay, what is next? Our main goal is to obtain differential equations, which help us to find this guy, but not this bear guy, but renormalized green function. So to this end, for now, we will rewrite this definition actually together with this definition in terms of only renormalized quantities. So what we will see is the relations between renormalized green function and Bayer green function, this and this, and we rewrite this derivative in terms of renormalized quantities as well. Okay, let's start. So the most general choice of relations between Bayer and renormalized field, coupling constant, mass is as follows, given by formula 1. We know that in phi 4 model, we also have relations between renormalization factors for coupling and for renormalization of the field, and renormalization factors of two-point green function and four-point green function. So let me talk a little bit more about renormalization of green function, of n-point correlation function. We know that actually the definition of these z factors, renormalization factors, come from the action of R Bogolyubov operation on Bayer green function. And this action and definition, or yes, definition of these factors given by formula 3 on the slide. So as usually, R prime subtract the divergent subgraphs and K operation reflect the overall remaining divergence. What it means? Let's consider the simplest case of minimal subtraction scheme. where we know that divergences enter as 1 divided by epsilon. So this operation K will return only this behavior, these poles, and R prime subtract the divergent subgraphs or subdivergences. However, this the most general formula how we can define renormalization factors. However, it turns out that in the framework of finite QFT, in the framework of Callan-Symanzik method, it turns out that we should think how to deal with subdivergences, because if you consider two loop diagrams with subdivergences, for example, something like this one, you immediately find out that you may act with many theta operation, but you never kill the subdivergency. So what to do? Actually, it turns out, and Callan told and taught us how to deal with this situation within his Callan-Symanzik approach, is to use so-called skeleton expansion. It means that you just never take into account diagrams where you meet subdivergences. You should consider only diagrams which never have this situation, these subdivergences. On algebraic level, this means that you just put R prime operation equals to 1, and presumes that subdivergences are not subtracted. And this is this reflects the skeleton expansion formalism. And we will stick to the definition of our renormalization factors, Zn, which is given by formula 4, but not 3. This is very important point for Callan-Symanzik method.
Excuse me,
Okay.
can I ask you,
Sure.
tell us this, it's kind of, you do have diagrams with subdivergences, right? In the
Yes,
quantum field theory.
yes,
And
yes.
what do you mean by skeleton expansion? I just forgot probably the standard thing,
Okay.
but nevertheless, do you throw away these diagrams? Do you distort quantum field theory somehow? What do you do?
Yes, I mean that I should take, for example, only diagrams at one loop. Surely they're very simple and it's not so interesting. But then we turn to two loops. Actually, here we don't have anything, because this one has subdivergency. Yes, the
Yes.
penguin also has subdivergences, etc.
Yes.
And
So what?
it means that in this formalism, you need to consider the following thing. You should consider this diagram fish, but with renormalized from the previous order, new vertex, renormalized from the previous order. Or, for example, consider renormalized from the previous order from one loop for propagator.
So
This
you mean that you have already subtracted the subdivergences, right?
Yes, in this way, yeah. But you cannot consider these diagrams because you cannot win. You cannot kill the subdivergency using theta operation, unfortunately.
Ah, okay, okay. So you mean that after prime you have already acted by R prime on
Yeah.
the on your graph,
Yes,
kind of.
yes, yes. Yeah.
Okay, thank you.
Okay. Thank you for questions. Okay. Let's go next. What is next? Oops, sorry. Okay. We consider field, coupling constant, mass, and write down as well as renormalization of green functions. But in this formalism, we have also functions on which we act with theta operation once or twice. So actually, we need to think how to renormalize them as well. And one of the simplest way to renormalize them as well is to introduce something like z theta. Actually, how do we know that we should write down here z theta squared, here once, here also only one this factor? For now, this is the experimental observation, which we understand only after evaluation or application of this Callan-Symanzik method to this 5-4 theory. But I guess that then we consider other theories, more complicated, non-renormalizable, or the theory with more fields, we may think and understand some recipe or scheme on how we should write down here the correct factor which equipped us with the renormalization of these functions as well. But for now, this is a question. So for the theory of quartic self-interaction, I know the answer, but about any other theories, we should think about it. Okay, for now, we have everything and we are ready to write down differential equations, Callan-Symanzik differential equations. What we do is rewrite this derivative with respect to bare mass squared in terms of renormalized mass and renormalized coupling constant. And what is nice and what is the new thing which we have found with Andrei Lvovich, that for now we write down explicitly these renormalization factors, rewriting this derivative and write down explicitly and in a very general manner all renormalization of all things that we have in this sphere: field, mass, coupling constant, and all green functions. They come with very general their renormalization factors. Okay, now let's substitute formula 8 to this formula together with all relations from the previous slides, which relates bare and renormalized green function and green functions with theta operation. Then we substitute here formula 8 and rewrite both sides in terms of renormalized things. We arrive to the following quite simple system of Callan-Symanzik differential equations. And after some algebra, we also obtain here some coefficient, which turns out to be beta function, anomalous dimensions of green function mass or field, and everything I have here are finite things. All these left sides contain by the definition or how we obtain them finite green function with theta operation. You see that, for example, if we act twice with theta operation on one loop two-point correlation function, we obtain something finite. So, okay, here we will use this diagram, this expression with two theta operation at one loop level. And later we will see how this work. Okay, you may find this system of equation or something similar even for quantum electrodynamics, for theory with phi 6 plus phi 4 model, as well as in models with two scalar field with different masses. Very similar equation you meet everywhere, and you may obtain them in the very similar way as we see on the previous slides. Okay, what is new on this derivation is that for now we have inside these factors very explicitly all renormalization factors. So we see where all, I can say, divergences sit actually. They hide something here. Okay. After that, as we write down equation, we another important thing I should say here is that then we derive this equation, we arrive to the formulation of beta function together with all anomalous dimension, which are formulate with in the presence of renormalized mass and renormalized coupling constant fixed. This is very important because then you write down renormalization group equation, you can obtain equations where you define beta functions with fixed bare mass and bare coupling. So this is very important that in this approach we obtain explicitly these definitions of all beta functions. And very interesting thing that we meet is that coefficients in expansion of this beta function together with anomalous dimension given in the previous slide does not depend on the renormalization scheme. However, then you consider the situation with fixed bare mass and bare coupling constant, the situation is opposite, and this coefficient of then you expand beta function and anomalous dimension, they depend on particular scheme. So this also opens up a possibility to study some technical details of this approach, and I will talk about them later. Okay, as you have this system of differential equations, you can solve them, but it is not enough to have only equations. You need to have, for completeness, to define integration constant, some boundary conditions, and they are nothing but the choice of renormalization scheme, actually. So together with renormalization boundary conditions, you can indeed you can obtain finite in a fully finite way 2-point and 4-point green function. And the next slides are dedicated to evaluation of this guy and this guy in the simplest toy model with a 5-4 self-interaction. So let's see how all it works. For now, and actually in the modern literature, this method was considered at one loop level, and it's very interesting what happened, and it's very interesting to understand all details. For example, the use of skeleton expansion, accurate and explicit use of skeleton expansion at the level of two loop. It was not done explicitly. So for now, I can talk confident only about one loop level. So as it was stated many times, we have bare 4-point function in this form, and this integral is divergent in logarithmic way, and we need to act one time with theta operation to make it finite. So let's do it. And what we obtain, actually we obtain the left-hand side of our Callan-Symanzik equation. We obtain this guy. Having it, we can solve this equation together with boundary condition. And we really need boundary condition because here we actually have some unknown for now coefficient beta and gamma. We don't know what is it. Okay, let's see how we work out this equation. So, as I already said, at the lowest order in one loop level, we obtain finite expression for gamma 4 with theta operation. It is given here. So, let us consider this equation at boundary. I mean, let us consider this equation at, for example, zero external momentum. What we obtain from this equation? Just substitute kappa, eta, these are external momentum, equals to 0 everywhere in this equation. We know that, we know this one, it equals minus imaginary unity multiply lambda in all orders of perturbation theory. So we substitute here minus E cross lambda, and we need to leave everything at the level of lambda squared. Why? Because we find out that we have at one loop gamma for with acting of one theta operation proportional to lambda square. So that's it. Our left-hand side is proportional to lambda square. So let us to obtain, to be self-consistent, something proportional to lambda square on the right-hand side. Okay, that's it. We substitute also everything on the right-hand side at zero external momentum and arrive to some nice condition which comes from boundary condition or from our renormalization scheme. After that, we take this expression and substitute it in our equation again. After that, what we find out? We find out that we have some nice relation between beta and gamma here. We know this expression, so it means that we know all coefficients in this expression at one loop level. And after that, we may integrate with respect to mass square and derive finite gamma for green function. So that's it. This is our inverted Callan-Symanzik equation as an integral over mass square. For now, I don't write it as an integral, but at the end of the day, surely we just take this integral from the right-hand side. And finally, we find out something finite, and we never meet something divergent through all the way of calculation. This is very standard and very well known answer from the standard approach to QFT, so we match with it, and I guess it's nice cross-check at one level. Okay, in the same way, we can derive two-point correlation function in the same theory. What we do, we again consider this diagram, and oh, sorry, this one, but act twice with our cross vertex. And this is nothing but this answer.
Julia, excuse
Yes.
me, may I interrupt
Yes.
you, ask you a question? What do you think, whether it is possible to consider at this step, at the one loop level, the subtraction, not at the zero external momentum, but at the definite subtraction Euclidean point or some mu square?
I
What's
guess,
your
yes.
opinion?
Yeah, surely you can use. What changes is that, okay, is that you should use another boundary condition here. So you fixed your.
In some sense, not
Yes.
here, but here, cos square is not equal to
this
zero, but cos square is
Yes.
equal to mu square.
Yeah. You just change your boundary condition, and after that, all integration constant
fine.
also change. For example, here, and it leads to some other answer here as well. So if you change your boundary condition. Okay. Let me draw again this diagram, but actually I guess that you catch the idea, but nevertheless. So this diagram with the two crosses fully finite, and again in the totally similar way as for four-point function, we again take this finite answer, and this is nothing but our left-hand side in Callan-Symanzik equation. What is very important here is that you should calculate or solve these equations together. because, for example, if you start with this equation and forever forget about your 4-point function, you can never solve 11 equation, because the solution of previous equation for 4-point function equips you not only with finite 4-point function, but with a useful relation between beta function and anomalous dimension. And actually, you use it in this equation as well. So proceeding fully the same steps as for 4-point function, at the end of the day, you also obtain some interesting and useful relation between also this guy, and this. And substituting this back to equation, you arrive to, for this equation, for 11 equation, you find out gamma 2 theta, and substituting this function into the last Callan-Symanzik equation. Let me show you this equation one more time, because I guess it will be more clear. So from this one, you find out firstly the relations, another relation between all these values, or you find that gamma theta actually equals 0 at this one loop level, etc., and find out also gamma 2 theta. After that, you turn to the last equation on this slide, substitute found gamma 2 theta on the left hand side, and again consider this equation on boundary with boundary condition, and find this 2-point correlation function at the end of the day. So this is how all it works. The main ingredient is that you should think about your loop expressions and understand how many times you need to act with theta operations on them in order to write down the left-hand side of Callan-Symanzik equation. So you need to know how your integrals diverge in your theory. So for now, I guess it's not so convenient, because then you start to apply Callan-Symanzik method to another model, to another field theory, not 5-4. You again should remember about standard approach. You again you need to know which divergent integrals you have, how they diverge. And after that, you can understand something about Callan-Symanzik equations, how to derive them, how many theta operation you need, etc. But I get that there is some also scheme or receipt, and we can think about it, how to write down some general scheme of how to understand how many theta operation we need for each separate theory. Okay, let me move forward to another technical thing related to this Callan-Symanzik method. You may think that these equations, even they called as Callan-Symanzik equation, actually they are nothing but or very similar to standard renormalization group equation, because we usually call renormalization group equation also as Callan-Symanzik equation. So what is the connection between these two methods? You see, the first difference is that renormalization group equation, this is one equation. But in Callan-Symanzik method, we have at least two differential equations for 2-point function, for example, and one for 4-point function. But anyway, we have this difference here. So what to do with it, and how they relate? Because another difference between these methods is that you see that in Callan-Symanzik method we have derivatives with respect to mass and with respect to coupling constant, etc. But there is no the derivative with respect to some scale mu which we usually meet in renormalization group equation. So let's think about these and other difference between these two approaches. First of all, let me choose a little bit other conditions for which we define a renormalized mass and coupling constant. On the previous slide, I take very simple conditions at zero external momentum, sorry. But here, let me introduce some scale, mu scale here, and let me consider and define lambda constant in this way. And let me refer to this as to momentum subtraction scheme at some scale mu. Next, let me also rewrite the condition on the definition of physical, or no, sorry, not physical, renormalized mass as follows. Also on some scale mu. I'm sorry, here I write down already m. So let me clarify this moment. So here we can write down gamma 2 in terms of some indefinite mu scale as well, instead of mass. So imagine that here I write down mu. Sorry. Then here we, for this guy, if we write down instead of m mu, imagine this one also, we define renormalized mass as follows, something like this. Oh, sorry. Mu square minus m square. So this is my renormalization condition for, I don't care for now about...
Sorry, be careful.
Yes.
Sorry. Personally, I think I propose you to think about adding mu square, the scale, to sigma. Not p square minus m square is fine. It is one.
Yes.
It is appearing. So mu square may appear in your notations. Probably you missed it. In sigma, pi square, m square, lambda, and put there mu square, and then putting mu square equal to. Okay, do you understand me?
Yes, sure. I try to clarify this moment as well. So imagine that here we have mu.
The problem of notations.
Yeah. Because actually at the end of the day, I want to put this mu square to m square, and this will be my on-shell renormalization condition, this one. But actually I can write down renormalization condition for mass in the same way as this one, with some general scale mu. So for now, I try to write down something like this. Okay, let me write down gamma 2, which depends on p square equals to not to mass square, but to mu square. So if I don't think about something like this, I actually should write down this condition, mu square minus m square, and then I send mu square to m square and write down my this formula in box. I immediately arrive to this condition, and this is how I define renormalized mass. So this is my wish to write down to this condition, because for me, for now, it will be convenient to work with these conditions for now. And actually, we need to fix residues as usually. That's why we have the third renormalization condition, which usually connected with differentiation of gamma 2 with respect to momentum. And we can choose it as follows. So what we learn from this slide is that for now, for my next purpose, I fix momentum subtraction scheme for coupling constant, this one, and I fix the following on shell because I take p square equal to m square for renormalized mass. And using this boundary condition, let me go further and consider both standard renormalization group equation and Callan-Symanzik differential equations and understand, are they the same things or not? So let me kill all my pictures and go next. So all we familiar with the equation, with this renormalization group equation. But for now, I write down it in terms of beta function and all anomalous dimension with fixed renormalized mass and lambda. Xm is nothing but this notation xm equals or defined as m divided by mu. So don't be scared with this notation. They are nothing but some massless variables. Sometimes it's convenient to use this one instead of separate mass and mu scale. So introducing these notations. Why I introduce this notation? You can guess it easily, because if we think about Callan-Symanzik equations, in this differential system of equations, we also have beta function and all anomalous dimensions defined with a fixed renormalized mass and renormalized coupling constant. That is why I want to write down renormalization group equation also in terms of something similar, because I would like to compare these two approaches and understand, are they similar or not, no, and why, if they different by some I don't know. For now, we don't know. Maybe these two approaches are very different, but maybe renormalization group equation and the Callan-Symanzik system of equations are totally the same. For now, we don't know it. So let us compare these equations term by term. We introduce everything, introduce beta function and introduce renormalized green function in both approaches. Okay, let me also write down the Callan-Symanzik equation. For now, I write down only one equation. However, we have the system. So let me clarify this moment here. We should think about this point as about the following thing. You start with a Callan-Symanzik equation where you have gamma 2 with 2 theta operation on the left-hand side and with gamma 2 with 1 theta operation on the right-hand side. Then you evaluate this, work out this equation and find out gamma 2 theta. After that, you take it and substitute it here. And it means that actually you can consider, then you compare Callan-Symanzik equations with renormalization group equation, you can consider only this one equation. So this is our explanation of how to compare renormalization group approach and Callan-Symanzik differential equations system approach. Okay, the same we do with 4-point function, but there we have already one Callan-Symanzik equation. So things are simpler in this case, but I clarified a moment about 2-point function and two differential equations. Okay, the definitions of all beta and anomalous dimensions I again repeat here. And what we want to do, for example, let's see, in Callan-Symanzik equation, we have something unusual. We have a 2-point correlation function with action of theta operation. So, but in renormalization group equation, we don't have any like this.
Yulia, and fixed, renormalized mass and lambda.
Yes, in both equations, sure.
This is
sure.
yes. at this stage also. This is
Yeah.
boundary conditions here are rather important. Yeah, you
Yeah.
understand, but just to add, to clarify to the community.
Yeah, it's very, as I already said, that then I write down renormalization group equation. I said that everything is write down with fixed coupling and mass. And the same as in previous earlier slides,
Renormalized.
we also with normalized,
Very
yeah,
important.
with normalized
Renormalized.
mass and coupling constant. It's very important. Okay, after that, let us consider the most interesting and intriguing term, because we have this one in finite QFT approach, but we don't have something something like this in renormalization group approach. So what happened? Maybe due to this term, these approaches are totally different, or no, we don't know. So let's see. If we take this term from Callan-Symanzik equation and start to rewrite it in terms of all bare values, and remember the definition of anomalous mass dimension, at the end of the day, we find out that the renormalization factor for mass just cancel through evaluation, and we arrive to nothing but this thing. And we find out that within chosen renormalization scheme, renormalization conditions, we arrive to something similar to this guy from renormalization group equation. So if we expand this tilde gamma anomalous dimension of mass, we find out that within mu scale equals to mass, this just unity, and our first term of Callan-Symanzik equation just similar or relates to this term from renormalization group equation. So this term is the most interesting because we don't have the obvious analog of this in renormalization group. But if we think about all other terms, for example, term with beta function, surely we have this one in Callan-Symanzik equation, and we have something similar in renormalization group equation. And we find out, if we expand both definition, they are different. We have different definitions of beta function in this approach, in the renormalization group approach, and definition of beta function in Callan-Symanzik. They're somehow different. But then we start to substitute mu square equals to mu square. It means that we consider scheme with on-shell mass. We find out that these terms just the same. Also, what you can immediately say that here I have lambda square, it means bare mass, bare coupling, sorry, and here I have finite renormalized coupling. And you're right, it means that Callan-Symanzik equation write down in a very specific scheme where we have z lambda equals unity s equals 1 and zm equals to 1. That's why we don't scare these terms with lambda 0. And that here we also have renormalized lambda. So what we take home from these two slides, we find out that renormalization group equation is totally the same as Callan-Symanzik equation, only in the case of the choice of specific renormalization scheme. Then we take this scale equals to mass, and then we consider very specific prescription, very specific renormalization scheme for coupling constant and mass. Only in this case, only in this choice of renormalization scheme, on-shell condition for mass and momentum subtraction for coupling constant, we find out the equivalence of these two approaches, but they are not equivalent in general. So we learn that Callan-Symanzik method is just the choice of concrete renormalization condition. This is a concrete renormalization scheme. That's it. So, okay. The last thing I would like to tell you is that we try to consider and apply this Callan-Symanzik method to theories, to non-renormalizable theories. For example, theory phi4 plus higher dimension operator phi6. In this case, we obtain another beta function for this coupling, and actually we can derive the generalization of Callan-Symanzik equations. In this case, we need one more Callan-Symanzik equation for 6-point correlation function for something like this, and subsequently solve equation for this guy, and together with equations for 2-point function and 4-point function, and taking into account all needed diagrams, we may restore or we may obtain known results from which matches with standard approaches. Actually, also we can solve this equation at one loop. Sorry, it's very important. Again, I can talk only about one loop. So we can obtain answers which matches with standard QFT approaches. However, it's very important that we don't know what happened on higher loop. It should take more work and more accurate considerations, but at one loop it seems that everything is okay. Another remark which I should do here is that Callan-Symanzik equations, which are written for this theorem, we write down them already from the very beginning in very specific renormalization scheme. It means that we consider from very beginning that z lambda equals, oops, sorry, it's not so convenient to draw from trackpad, equals 1, z for mass equals 1, and z renormalization constant for this coupling constant for phi6 equals 1. So we consider from the very beginning this renormalization.
Yulia, sorry, be careful at this stage. We're just discussing with you, because when you're adding G6, G56, this is non-renormalized model. And here, that G is equal to 1 is a little bit, we should be more careful in defining this point.
Yeah, sure. I talk only about one loop.
The first two definitions are fine, but the final definition, it is better to be very careful here, because we're coming out of renormalized models to renormalized plus non-renormalized. And here the definitions of analogies of renormalized coupling constants are very careful. So I would agree that the first two definitions are fine to one, and the final with question.
Yeah, sure. And all its methods for non-renormalizable theory for now it's very I don't know how to say very thin things. So we should consider it in a more accurate way. Write down general. I mean, taking into account these guys in a general manner. So we should define beta function for lambda and beta function for this coupling in a more general way, taking into account these renormalization factors explicitly, not equals to something. So, however, we try to apply this method, this nice method, to other theory, and at one loop it's okay, but surely there are a lot of questions, and we should do more accurate work about this method applying to other theories than phi4. And actually about phi4 we also should carefully think about what happened at two loop level. So let me go to the end of my presentation, to the discussion. During the past year, we rewrite Callan-Symanzik equation and take into account all renormalization factors explicitly. We find out that we arrive to fully the same Callan-Symanzik equations as Callan has obtained them, and as Mikhail Evgenievich Shaposhnikov also obtained this equation in the same form. However, he started with the choice of concrete specific renormalization scheme from the very beginning, and we carefully take these Z factors, renormalization factors from the very beginning, and explicitly include them in the definitions of beta function. And why we would like to take them till the end, till the very end, because this opens up a possibility for us to accurately compare Callan-Symanzik equations with renormalization group equation. And this helps us to understand what is Callan-Symanzik approach is. Actually, this is nothing but some renormalization scheme. And the most important thing that this is on-shell renormalization prescription for mass and momentum subtraction for coupling constant. So this is very interesting and important point about this approach. What we can do further? We find out that on-shell scheme is somehow distinguished in this approach, and we know that this scheme actually distinguished in many theories. And for example, we can consider our setups where on-shell schemes also used and distinguished, and we can try to understand what does it mean. Is it just coincidence, or is it does it mean something deep and some physical content? Does it have some physical content, or just a coincidence? For some theories, we surely know that yes, they distinguish because they are physical, but for other, we don't know it. So next, we can consider Callan-Symanzik method for massless and gauge theories, and here we surely face some difficulties, because you see that in this approach we have differentiation with mass. So what to do in massless theories, it's actually a question. However, we know that Blair and Yan also in 80s from the past centuries apply this method to quantum electrodynamics. Another set of question and the realization of on-shell scheme and in general realization of Callan-Symanzik approach to QCD is also very questionable. So we must be careful when we apply this method to any other theories, not 5-4. Another result on this topic is actually that in 5-4 we have all answer matches with standard approach at one loop, and the same for theory with two fields, one light and one heavy. Also everything is okay at the level of one loop. However, we should carefully think about the level of two and high loops. For now, we don't have explicit, careful calculations on this point. And also at one loop level, as I already told, we consider phi 6 model as well. Many comments I already said about it, so here let me go to the next slide. About more loops I already said, and very important point here is that we should understand how to correctly use skeleton expansion and use it, and carefully proceed everything with, for example, two loop level in any model. Okay, any new insights and comments are super welcome. Thank you very much. And the last word I would like to set is that what is the motivation of all this approach, to consider all this approach? Actually, the main motivation is the naturalness problem. You know that if we consider Higgs mass, physical Higgs mass, let me write down something like this. I I consider only Higgs mass squared, and then I start to evaluate one loop correction to it. I find out that this one is 3 mass plus something from one loop level, delta m square, one loop, sorry, I hate trackpad. Okay, and we know that it is proportional to lambda squared, some cutoff of the theorem. It may be the mass of top quark, it may be Planck mass, anything you want. So we know that the mass of Higgs from experiment, and at the end of the day, we see that there is some fine-tuning between this very huge, large contribution from one loop level, and we need to obtain around 100 GV on the left-hand side. So we need to somehow fine-tune these two guys, and it means that our lower energy scale somehow sensitive to UV, ultraviolet, very huge energy scale. And this is the nutshell of naturalness. However, if you don't have this one, I mean, cutoff scale at all, for example, you don't have one loop divergences in Callan-Symanzik approach, it immediately means that you don't have a naturalness problem in this approach. So Callan-Symanzik approach may be thought as a resolution of this problem. However, I should comment that it at the same time does not somehow comment why we even have very different scales in physics at the end of the day. It's just solve this strange fine-tuning of these different scales. For example, if you take Planck mass here, you need to somehow fine-tune your these two values to around 100 GeV. Planck mass is about 10 power 19 GeV, and here you have only 100, so it's a terrible fine-tuning. Okay, this is the main motivation for this approach, and for me, it's just a very beautiful mapping between something found from the very beginning, because from the very beginning, we don't know that Lagrangian must include something huge, some counterterms, and so on. And at the end of the day, we also obtain finite cross-section. So if we can invent approach where we have all finite during all the way of calculation, it's very beautiful from my point of view. So thank you very much. All comments and questions are welcome. Thank you.
Okay.
Can you hear me?
Yes, we do.
Okay.
So,
Okay.
okay. Let's start with
I
the
have
questions.
a very brief question. This approach is still perturbative, right? So
Yes.
it's all in perturbation theory, because in principle you can dream of some other approach, well, like lattice or something which defines theory or non-perturbatively and provides a cutoff. Yeah.
It's perturbative again, because you see that I consider one loop level. It means that I consider expansion with respect to h bar,
Yeah.
or coupling constant level, expansion with respect to these guys. Yes, so it's purely perturbative, surely.
Okay, thank you.
Thank you.
May
Yulia,
Arkady, excuse me. But of course, on the lattice, you have also the regions where you have perturbation theory, and you have the matching of the non-perturbative calculations with perturbative calculations. But there in the lattice, you have the regularization, the cutoff. The lattice space thing. So in principle, your question is rather interesting, whether it is possible to consider this approach in the case of, say, lattice regularization.
Yeah,
Thank you very much.
I agree. That would be interesting. Yeah.
Yeah, thank you very much.
Yulia, may I ask a question?
Sure.
Thanks a lot for a nice talk. Actually,
Thank
I
you.
have a couple of questions, but they are very much related. One of them is, I just wonder whether this approach to making field theory finite give you any intuition on what quantum fields are like. Because there's a big problem of a mathematical rigor of quantum field theory. There is, like Weizmann theory, Weizmann axioms, which announce that the quantum field be defined in a way like some operator value distributions and so on, in order to completely rule out, just resolve all those divergences and absence of mathematical rigor in all the calculations. So is this approach able to somehow give us the direction in which to move? And the second question, which is much related to the first one, and also related to the fine-tuning thing that you mentioned in the very end of your talk, I wonder, there is the problem of quantum triviality, which basically means that if you, within just a standard renormalization group approach, if you set the cutoff to infinity, then the theory, and then if you normalize your couplings to some finite values at this infinite cutoffs, then in this earthly world, so at finite momenta, your couplings become zero. So your theory becomes free. That's called quantum triviality. So am I right that because within this approach, you don't have the cutoff in your equations, you have just the physical mass or renormalized mass and the physical or renormalized, but as I say, renormalized coupling, then there's no such problem anymore. So your theories are not trivial at all. Say quantum electrodynamics becomes trivial if you say set the cutoff to infinity.
Actually, about the second question, I should think, because it's interesting question about triviality. Indeed, we don't have any cutoff here. So your question is what happened with what? With green functions when you send lambda?
Yep, for example, because you can relate them to, say 4-point Green's function to some coupling.
But maybe in this sense, if we directly arrive to something finite using this approach, everything is okay. Or maybe this question, we cannot ask this question within this approach.
But that's good. That's good.
Yes,
because this could be one of the answers to this question. Because, quantum triviality is one of those things for which mathematicians usually blame us, physicists. They say your quantum field, your interacting quantum field theories simply don't exist. Like if we follow some rigor, then they become trivial. That's what they say sometimes. If they are not effective theories, I mean, truly quantum field theories without any scale at which this theory is not gonna be adequate anymore. And one more remark, just one sentence. There's been some recent progress on some efforts regarding defining a rigorous measure for phi-4 theory on the lattice exactly.
Okay.
So I think it was Euclidean space-time, which may be quite important. But anymore, over the past, I think, 5 or 10 years, I saw just a couple of papers. So it's a nice idea, in my humble opinion, also to try how they could live together, Callan-Symanzik and lattice
I
regularization.
see. Yeah, it's nice idea. Okay. And about your first question about how we define the scalar field, can you expand it a little bit?
Yeah, I mean, in quantum mechanics, you have a well-defined Hilbert space. You have a well-defined, you say, like the closed symmetric operators defined and then subspaces of a Hilbert space, which render all the scheme using which you first solve the evolution equation, the Schrödinger equation, and then calculate your expectation values of the observable. It renders it all mathematically rigorous. But this works in finite dimensional space and for mechanics. So quantum mechanics. When you go to quantum field theory, it all becomes a little bit more complicated because what is the quantum field operator? What is phi? This is the central question. What is the Hilbert space in the true quantum field theory? Not the perturbative, physics-like approach of it. Just what is the space? And there are certain limitations like the Hawk's theorem that say that you can't do it, in a very straightforward way. So this was my question.
So I guess that all what is relates to this definition and these things about scalar field, I guess they are totally the same as in a standard approach.
I
so
see.
we define scalar field in totally the same way. Okay.
Thanks a lot. Very
Thank
inspiring.
Thank you.
Comment to comment.
Sure.
In fact, your question is rather interesting because your question raises the question, what is the field? Whether this field is renormalized or whether this field is the bare one. Because in these considerations, Yulia just discussed, there were two languages. The first language is the renormalization group technique, where when everything is renormalized and the boundary conditions are fixed by the bare coupling constant and bare charge fixed. But when we are speaking about Callan-Symanzik method, we are starting from another point of view. We are starting from the consideration when everything is the bare one, but in the definite moment when we are coming to the analogy of the renormalization group equation, in the beta function with the wave, gamma function with the wave, there the boundary conditions are defined with the fixed renormalized bare coupling constant and bare mass. And therefore, your question, for example, what is the free phi for the fourth theory of quantum electrodynamics, then we may ask the question whether this definition is on the bare language or renormalized one. And this is rather important. And these considerations Yulia presented may help to make the bridge between these languages and between these questions, which you are raised sometimes without careful definitions of these boundary conditions. Whether I managed to just clarify some points to your question or not?
Yes, I think you have.
Okay,
but there's a lot of discussion that may follow. That's interesting.
Yeah.
Inspiring. Thank you.
Yeah, great.
Thank you.
Excuse me, regarding Oleg's question about Landau pole, I should comment that I doubt that Yulia and Andrei Kataev and other people, they will in such a simple way. They don't pretend even to solve the problem of Landau pole, and I think that they don't want to solve the Landau pole problem because they basically restore the standard results with a new technique. And in the standard result, you do not have to impose a cutoff to observe the Landau.
Better to say it cannot be solved.
Yeah, I mean, probably. I just was trying to be polite. Okay.
Yeah.
Okay. So you don't need to impose a cutoff to see the Landau pole. You can use renormalization like they do,
Oh, sure.
like MS bar technique, for example,
Sure,
or
sure. It's
any
just the
kind of
trajectory,
yeah,
right? The RG trajectory.
But in this language, you will see Landau pole in the following sense. You will see that the theory will become non-perturbative, that the higher order corrections will become a order of lower order corrections at the scale comparable to the Landau scale of momentum, right?
Yep.
And you will resum these large terms, this renorm group technique, and this will not help. You will see that your renormalized green function, which is in their case is the same. Renorm group improved. Okay, green functions you'll have a singularity at Landau pole. So
Oh, yes.
yeah, so
Yeah,
that
so
story is
actually
basically.
maybe, Dmitry, thank you for your remark. I just, maybe I didn't formulate it clearly. Well, I meant maybe there is some new perspective that this approach could give, you know, on the very problem of the Landau pole and the rigorous definition of quantum field theories. That was my point. Of course, I didn't mean that, you know, with that you could solve it just in one shot.
Yes, it's a question for now. Yeah. Yes.
Okay, can I ask a similar question to Alex's one?
Yeah.
Then,
Yes.
there is another problem like a renormalization of a composite operators in quantum field theory, right?
Okay.
For example, you can have a complex field phi and operator phi to the n power. This is
Okay.
so-called large charge operator. And at large n, there is a problem with this finding its anomalous dimension. I wonder whether your equations, Callan-Symanzik
How they manage
equations,
this?
can they manage this? Can they make this better, or this is just a standard story as well?
Maybe, but I don't know precisely. I guess that I should see more accurate and write down equations for this theory and see what happened inside, for example, inside beta function anomalous dimension. For now, I don't know what happened in such kind of theory.
Thank you.
Okay,
But probably you do know, because in fact, the composite operators may be as fields defined on the Bell language and on renormalized language. So your question, Dimitri, is whether these methods may help to clarify how to evaluate these questions within the one method or another method, because we may write down just the same operator, phi zero, and this is the composite operator. So thank you. We should think about this question as well, how to clarify this point to you.
Well, yeah, basically, I meant the operator phi to the nth power, where n is large.
okay.
Okay, that pion is even more complicated here.
Sure.
Thank you.
Thank you. Okay.
Okay, well, if there are no other questions, I'll bring up my rather naive question about
Okay.
application of this technique to non-renormalizable models. So,
Okay.
so again, which non-renormalizable theories have you tried to disentangle this way?
This one by 4 plus with lambda. I don't write down explicit coefficient, number coefficient, and another coupling constant divided by some new scale big M multiply phi 6. This case we have considered at the level of one loop only.
I see. Interesting. Yeah. And well, in comparison to other techniques, I mean, because well, we will hopefully we'll have these term people who will talk about resurgence and renormalance. How strong do you think, well, your technique is to, you know, to make the theory somewhat renormalizable? Or is it all perturbative and my question is absolutely inapplicable?
Sorry. So your question is about is it easier to calculate thing within our approach or another question?
Yeah, yes, and can the approach make the theory? Oh, yes, sorry. Yeah, sorry. Now I understand. Yeah, of course, because you're working perturbatively, you cannot make theory well renormalizable. So yeah,
Yeah.
sorry.
Yeah.
Yeah.
And
Then the question was also about renormalization. In fact, this is the correct question concerning this model. But in this case, of course, these considerations may help to understand how renormalization contribute may be taken into account within Callan-Symanzik method. But in the case of lambda to the 5-4 theory, because the non-perturbative, this non-renormalizable attraction, the second coupling constant, we do not know whether the renormals contribute there. But this is the right question. And the question whether I understood you correctly, Arkady, that the question is whether it is possible to take into account or to consider how renormals are may be taken into account within Callan-Symanzik method. When we
Yes.
have the chain of the diagrams, because
Yes, precisely. Sorry, Andrei. It's not Arkady, it's Sergey, the secretary of the seminar.
oh, Sergey, okay, Sergey, okay, excuse me. Yeah, okay, yeah, okay, thank you.
Mhm.
Nice question.
thank you.
Thank you. Okay, so no questions one, no questions two, no questions three. Okay, well, let's thank Yulia again. And
Thank you.
well, thank you, Yulia, for the beautiful first seminar, the beautiful start of this new term. So
Okay.
hopefully we'll see you at the next seminars. And okay, goodbye.
Okay. Thank you. Very glad to talk here. Thank you all for the questions. Okay.